All right, so today we have Christoph Uhlemann tell us about 3D defects in 5D SCFTs and F-maximization. Take it away.
All right, thank you very much. Let me start by thanking our organizer, Julius, for the invitation to give a talk here and setting this up, and to everyone else for showing up. Pretty nice day here. So I appreciate it. And the story I want to tell you about today connects the study of defects and extended objects in quantum field theory with the study of higher dimensional field theories and extremization principles along RG flows. It's a line of thought which started roughly 2.5 years ago with Michael Goodperle, and in a recent paper with Leo Santilli, who's here, we extended this in a number of directions, and that's what I want to tell you about today. So we have 3 main players in the game: defects, higher dimensional field theories, and F-maximization. And the idea to start it off will be to introduce these players a little bit, fix some notation, and recall some aspects which we'll encounter along the way. So I think we all like our extended objects, starting with Wilson loops as indicators for confinement, through lots of recent activity relating to higher form symmetries and such things, all the way to D-branes and string theory. They play a role in all the nice frameworks we're working with. And the kind of dimensions and codimensions of defects we get to consider are certainly constrained by the dimension of the ambient field theory. So I will throughout use the convention to refer to the theory hosting the defect as the ambient theory, to reserve the term bulk for holographic discussions. And it is certainly interesting. In string theory, we have a lot of room for defects, but in quantum field theory, we do too, especially in higher dimensions. And so my focus today will be on 3-dimensional defects in 5-dimensional field theories. So codimension 2 defects. And from a very general perspective, the most constrained case is when the ambient theory is conformal and the defect preserves some part of that conformal symmetry. Can't preserve the entire symmetry, but at least the part associated with the defect can be preserved. And that's a very constrained scenario then. We can also look at defect renormalization group flows. We can turn on relevant operators which are localized on the defect and trigger flows, which in that way are really associated with the defect we're looking at. And the most general scenario is when even the ambient theory is not conformal and there's no notion of conformal symmetry to begin with. Everything just flows. And the idea today will be to use string theory and quantum field theory methods to study these advertised 3D defects in 5D theories. And we'll encounter all of these scenarios for conformal defects, RG flows, and ambient RG flows. So that will bring together a few things. And the reason why we will deal with all of these kinds of flows is rooted in the nature of the ambient quantum field theories. So we're looking at 5-dimensional theories. And being in 5D means we're dealing with inherently strongly coupled field theories, to which we only have indirect access through field theory methods. Much of what we know about them, we just know from string theory. So that makes getting access to these theories through field theory methods a little more tricky. But of course, it would be wouldn't be right to not mention that these theories are very interesting. They unify many lower dimensional theories, and in which can be obtained through compactification. And in that way, studying defects in these higher dimensional theories has the benefit of potentially teaching us about defects in lower dimensions. I won't talk much about compactification today, but as a general motivation, this certainly should be mentioned. What we will have to deal with, though, is that 5-dimensional superconformal field theories, the theories we believe exist, are generally non-Lagrangian. They can emerge as UV fixed points of asymptotically safe gauge theories in the strong coupling regime. And then we have field theory access through standard Lagrangian methods. But that necessarily then brings us to discussing renormalization group flows already in the ambient theory at some level. So that's sort of the reason for talking a lot about RG flows. And when we talk about RG flows, some notions which immediately come to mind are those of monotonicity theorems and extremization principles. In odd dimensions, the central object is the free energy on the sphere, which can also be related to the entanglement entropy of a spherical region. And we know that for genuinely three-dimensional theories, the sphere free energy is monotonic along RG flows. Gives us a way to count degrees of freedom in a meaningful way. And that's very nice. We also know that in supersymmetric three-dimensional theories with a U1R symmetry, quantum field theories like to extremize their free energy by adjusting the choice of U1R symmetry. That already sort of hints at maximization principles. But both of these facts are about genuinely three-dimensional theories. And what I want to look at today are three-dimensional defects in higher dimensional ambient theory. And that's a different cup of tea. For three-dimensional defects in higher dimensional theories, an F theorem has been established only very recently by Cassini and friends. And that will be a useful guiding principle for some of the things we talk about. As far as the ambient theories are concerned, though, there are no general monotonicity theorems for the free energy in 5D. So we have pretty substantial circumstantial evidence in a variety of contexts. So this won't hurt us too badly. For the theories I'll talk about today, a somewhat broad study of monotonicity can be found in this paper with Martin Fluder. So this was sort of a lightning introduction maybe through some of the things that are broad context. And what I want to do now is give an outline sort of overview kind of perspective on the results we talk about and the rest of the talk. So what I'm showing here is a kind of cartoon picture of the kind of RG flows we will consider. On the right-hand side, in the right column, the ambient theories at the fixed point and really a conformal field theory at infinite coupling, so to speak, from the gauge theory perspective. And we can then, in the upper line, consider conformal defects, which preserve some conformal symmetry, or look at defect RG flows in this five-dimensional ambient theory. In the left column, we have five-dimensional gauge theories. These are now actually theories which flow, they're not conformal. And we can add defects to those theories by just coupling them to three-dimensional matter, which may be massless or may be massive. So in some sense, on the horizontal axis are ambient RG flow, and on the vertical axis are defect RG flows. It's a cartoon, but what I want to do in the talk is first use D3 brains and 5 brain webs to discuss three-dimensional defects from the string theory perspective and conformal field theories, and use ADS-CFT to calculate the defect free energies for these defects. In the second part, we'll then switch to the gauge theory perspective and use field theory methods, supersymmetric localization, and do a similar exercise, calculate some free energies. And what we'll encounter here are long quiver field theories. So we have a few quivers, and hopefully that will that way fit the general scope of the seminar series. And in the last part, we then want to connect these two perspectives using some form of F-maximization. So the main part are some exact results for defects extending along three-dimensional spheres inside an S5. And I want to point out that as far as extremization principles go, the part I'm indicating here, this is a flow which is opposite to the ones which are usually considered three-dimensional theories. We're flowing here from the infrared to the ultraviolet. Okay, so that is sort of a general outline of what's to come before people go back to checking emails. And now we'll just jump right in. So I want to start with the string theory picture, talk about 5 brain webs, and give you some pictures which are then substantiated or made more quantitative in the context of ADS-CFT. So the ambient theories we're looking at are 5-dimensional field theories engineered by 5 brain webs. So PQ 5 brain webs with D5s horizontal and F5s vertical, and PQ 5 brains at angles dictated by their charges. We have a simple example here for an SU2 gauge theory. engineered by this pair of D5 brains. And the general picture is that length scales in the brain web correspond to dimensional parameters in the field theories. In this case, the horizontal and vertical extent of this D5 NS5 rectangle translates to the Coulomb branch and gauge coupling parameters in the field theory. In the brain web, we then have no problem taking the UV limit of this non-renormalizable gauge theory that corresponds to collapsing all length scales here to 0, and we obtain an intersection at a point which engineers the non-trivial E1 CFT, which arises as the fixed point of this gauge theory. And what we want to do is play with generalizations of these theories. So the general picture is that every junction of 5 brains at a point, as indicated here in this example, engineers some 5-dimensional superconformal field theory on the intersection point. I'm resolving things slightly here just to indicate a little bit the structure, but the idea is this is an intersection at a point, and we then get a superconformal field theory which is characterized entirely by the 5 brain charges. We can do more interesting things. We can terminate these 5 brains on PQ7 brains in an interesting way to generalize the construction at orientifold planes, F-theory 7 brains, and those kinds of things. That's all very interesting to look at, but for today, I will focus entirely on theories engineered only by 5 brain junctions. These 5-dimensional field theories engineered this way may or may not then have descriptions as gauge theories along the lines of what we had on the previous slide. And if such gauge theory descriptions exist, there may be multiple ones corresponding to different resolutions of the junction and characterizing or capturing different aspects of the 5D CFTs. So that's the general scenario for our ambient, CFT. And we have a natural large N limit for this junction where we just take all the PQ5 brain charges of these 5 brain groups here to be large. If they're relatively prime, we have a single 5 brain with large charges. If they have common divisors, we're talking about groups of 5 brains with the same charge as in this example here. Okay, so that's the starting point. And what we now want to do is take this general class of theories and add 3-dimensional defects to it. So how do we do that? The construction I want to look at today is to pierce the intersection point of a 5 brain junction with a D3 brain, which extends along a 3-dimensional subspace of this 5-dimensional intersectional locus and has the remaining direction transversed to the 5 brain junction. This preserves some supersymmetry. We're breaking the n=1 supersymmetry of the 5-dimensional ambient CFT to 3D n=2. Which retains a U1R symmetry, which in this brain construction corresponds to rotations transverse to the D3 and to the 5 brains. So we have an R symmetry here. And the claim is that as long as this intersection pierces the junction right at the intersection point, we still maintain some conformal symmetry. Intuitively, this should make sense. There are still no length scales in this 5 brain junction dressed with the D3 brain. So the idea is these are conformal defects. And since the defect is codimension 2 in the 5D theory, we have a rotation symmetry in the directions transverse to the defect. All right. So based or sort of generalizing the picture from the previous slides, now the idea is that we can introduce mass deformations of these defects by displacing the D3 brain from the intersection locus. That introduces some length scales, but if we're only having one semi-infinite D3 brain, it can't just end in smoke. So the only way you can move it is basically along some of the external 5 brains. Those kinds of things all introduce length scales, which are only associated with the D3 brain and correspond to defect or G-flows. And the number of such deformations then is given by the number of these external 5 brains here, since we have to slide along some of those external 5 brains. And that gives us a first hint as to what we will expect to find in the holographic description. So that's the idea. That's the 5 brain picture. And the plan is to now switch gears and turn over to ADS-CFT and study these defects more quantitatively. Before going there, I want to add one more comment. We can compare the picture in the 5-dimensional conformal field theories with what we see in the gauge theories. So in this example here, we have the 5D SCFT engineered by an intersection of D5 and NS5 branes. The conformal D3 brane defect is pierces the junction at the intersection point. We have two mass deformations. That certainly starts to change if we do mass deformations in the ambient 5D CFT. So on the right, we have a gauge theory deformation where every stack of D5 branes between NS5 branes corresponds to a single gauge node. So in this example, we have 4 SU3 gauge nodes. And now the D3 brane can move along the entire brane web, which engineers this gauge theory, which is certainly a bit more space than we have on the left-hand side. In this case, the ambient theory describes an RG flow. There's no conformal symmetry to begin with, and no distinguished notion of a conformal defect. But we have the benefit of a Lagrangian description, and the idea later will be to connect these things. All right, with that, I want to sort of move on from the brainweb discussion and really go to the holographic duals and discuss some results for these developments. So the reason we can make some progress on these calculations is that we have a broad space of holographic duals for these 5-dimensional superconformal field theories. And so my next task, I suppose, is to introduce those a little bit. So that's what I want to do here. Generally, the geometry created by the 5-brane junctions contains an ADS6 and an S2, representing 5D conformal symmetry and an SU2R symmetry. And they generally take the form of a warp product over a 2-dimensional Riemann surface. Going ahead then and solving the BPS equations in type 2B supergravity with the requirement that we want 16 supersymmetries gives me an entire class of supergravity solutions which are expressed in terms of a pair of locally holomorphic functions, A plus minus, on this Riemann surface over which everybody is warped. I won't give the explicit functions, but the idea is the metric, the two-form fluxes, the axiodilaton, and the killing spinors are all expressed in terms of these functions, A plus minus. So this is the general class of solutions which we're working with. Everything is completely solved. Every choice of Riemann surface and locally holomorphic functions gives me a supergravity solution. And the task at hand then is to single out physically viable solutions by imposing regularity conditions. Things like only singularities which have brane interpretations, things like that. And for the holographic duals of the 5-brane junctions I have discussed in the previous part, it turns out that the Riemann surface can be taken as a disk, possibly with punctures. And the solutions are characterized by locally holomorphic functions with meromorphic differentials, which have poles on the boundary of this disk, which we're looking at here. And the residues at these poles precisely correspond to the PQ5 brane charges of the branes making up the associated 5-brane intersection. So we have a complicated geometry on this disk, but really the schematic picture is we have our junction blowing up the intersection point gives you this supergravity solution describing the near horizon limit. And the brainweb data is encoded in the residues of these differentials. So the functions A plus minus really are sums of logs, very explicit. And the location of these poles is determined in terms of the brainweb data by regularity conditions, which are algebraic relations for these positions of the poles. All right, we can extend this construction to include punctures on the disk with SL2R monodromy that allows us to realize PQ7 branes in the brainweb, or more general things, including orientifold planes and F-theory 7 branes. But again, for the examples today, I'm going to stick entirely with junctions involving only 5 branes. Okay, so what we have is this class of ADS6 solutions describing the near horizon limit of the 5-brane junctions. It's fully fixed by the brainweb data. There are no moduli, and they provide the holographic duals for the 5D SCFTs we've been discussing. All right, so one can phrase everything about the defects I'm going to talk about in very general terms, but I want to instead just focus on 3 concrete examples to make it somewhat relatable. The first example is something we've already seen, an intersection of M NS5 branes and N D5 branes, something we call the plus and M theory, corresponds to a supergravity solution with 4 poles here on the boundary of the Riemann surface. And I will leave it at the schematic form of the solution and not bother you with big expressions for the explicit geometry. The gauge theory deformation we also already discussed is a linear quiver where we have SUN gauge nodes terminated by flavors at both ends, and otherwise same rank for all gauge nodes. The second example is the what we call the YN theory. It's an interjunction of 2N NS5 branes and then 1,1 and 1,-1,5 branes. That corresponds to a supergravity solution with 3 poles on the boundary of the disk, representing these 3 groups. Can be given very explicitly. And the gauge theory deformation is, again, a linear quiver where we have a large central gauge node, which is unbalanced, has a Chern-Simons term in addition, and to both sides, the rank of the gauge nodes then just decreases. So the quiver is given here in the explicit form, but the idea is we have some additional features compared to the plus theory. The last example is the TN theory. Again, a junction of 3 groups of 5 branes, NS5, D5, and 1,1. And again, a solution with 3 poles on the boundary. These 2 solutions are actually very closely related, but the quiver gauge theory descriptions look very different. In this case, we just get a quiver with gauge nodes of increasing rank with a large number of flavors on one side, small number of flavors on the other. So this will be our playground to work on when it comes to showing pictures. All right, and now sort of with this out of the way and some explanation of the solutions, it's a fairly straightforward exercise to describe these defects. If we take a 5-brane junction and pierce it with a single D3 brane, a junction of a large number of 5 branes and pierce it with a single D3 brane, we expect that the D3 brane won't disturb the geometry too much. And so it is described as a probe D3 brane in these ADS6 solutions we've just talked about. And moreover, if we're having a conformal defect, we need to find some sort of ADS4 isometries to represent the conformal symmetry. And that eats up all the dimensions of the D3 brane. It extends along an ADS4 and ADS6 and is otherwise localized at a fixed point on the Riemann surface and on the S2. Nothing can depend on the ADS4 coordinates, nothing can flow. So this is basically the embedding. We have our symmetries manifest, the U1R symmetry, and the transverse rotation around the defect come from rotations around the point in S2 and from rotations fixing the ADS4 and ADS6. So this is a very straightforward embedding to find. The BPS conditions are still messy to deal with on account of the somewhat complicated nature of the background solutions. But at the end of the day, you find a very nice condition in terms of this pair of holomorphic functions, which I've just introduced. Now, I don't want to give sort of explicit expressions for these functions and coordinates and such. What you can do is you can characterize the point that is singled out by this condition geometrically. On the Riemann surface sigma, we have at each point an ADS6 and an S2. And this condition characterizes the point where the ADS6 radius is maximal, and that happens to be the same point where the S2 radius is maximal as well. And for the solutions we're looking at here, for regular solutions, there's exactly one such point where these where the ADS6 and S2 radii are at a maximum. So we get something which is very much in line with what we discussed from the brainwave perspective before. We get one conformal D3 brane defect for each 5-dimensional superconformal field theory. And schematically, in the solutions we've introduced for the plus, Y, and Tn theories, we find a single point where the D3 is sitting. For the plus theory, this is sort of, there is a reflection symmetry under reflections along the horizontal and vertical diameters, and the D3 sits exactly at the fixed point of both of these reflection symmetries. For the Y junction, there's one Z2 symmetry corresponding to horizontal reflections, and the D3 sits on this line. And in the Tn junction, there's actually a Z3 symmetry, and the D3 sits again at the fixed point. But this Z3 symmetry is not represented in the gauge theory, or is not manifest there. and so on. Won't talk much about that. All right, so this is the general picture.
Can I ask you a question?
Sure.
So if the D3 is not at this point where the radii are maximal, what's the dual thing? Is it non-conformal and then it will flow down to there? Like it will move?
Yes, very, very good. This is going 2 slides ahead.
Okay.
If you're okay with that, I just go on and feel free to jump in.
Yeah, thanks.
Okay, great. Good. So these are the conformal embeddings. These are only pictures, of course, but they're concrete expressions for it. And so we can go ahead and calculate stuff as promised. What we're interested in is the defect contribution to the S5 free energy. So what we want to compare is the free energy for the 5D theory on S5, including a defect, and the free energy for the 5D theory without defect. That defines for us the defect contribution to the free energy. And in this probe limit, this holographically just becomes the D3 on-shell action. So we have the point where it's sitting, and we can just calculate the free energy right away from that. Since we're dealing with conformal defects, the distinction between spherical and planar defects is just a coordinate transformation in this holographic context. In the brainwave picture, we talked about sort of 5D CFTs on flat space and planar defects, but now we want to switch it to spherical defects. And the only difference is basically to use global ADS instead of Poincare ADS. And for the conformal defect, that makes no difference. So we can just calculate the free energies, and I'll give you, without further ado, here the results. We have the plus, Y, and T theories. Left column is the defect free energy, the D3 on-shell action. And on the right column, for reference, I'm giving the free energy of the 5D ambient CFT. So what we see here is some patterns which are in common. We have the defect contribution is quadratic in the brane charges, M and N in the plus theory, N squared in the other two, and generally involves dilogarithms. For the plus theory, we have this constant C showing up, which is Catalan's constant, and also related to dilogarithms. So that's the general pattern for these results. For the 5-dimensional ambient free energies, we have a similar story. Higher degree polylogarithms now, but they are quadic in the brane charges. So what we see is, sure enough, this free energy here in the large N limit is small compared to the background free energy. So we're justified in using the probe approximation to calculate them. And there's some room to even look at large numbers of D3 branes without spoiling the probe approximation. So I won't do that in any way today. The point of these calculations is it gives us a clear target for field theory calculations and is a starting point for discussing renormalization group flows. And we'll come back to these expressions later. But now I want to go where Antoine was already wanting to go. And the idea now is we have some idea about conformal defects. And now we want to see if we can also match relevant deformations between the brainwave picture and this holographic story. So we were looking at a particular class of deformations where we displaced the D3 branes in the 5-brane junction in such a way that the U1R symmetry was preserved and this rotation around the defect was preserved as well. The only thing we broke was conformal symmetry by introducing a length scale. And now we want to do the same thing in the holographic context. And we'll do this for planar defects, just like we did in the brainwave picture. So what are we going to do? We introduce a more explicit coordinate system for ADS6. We have a radial coordinate R, and breaking conformal symmetry now means things get to depend on R. So what we're looking at is a D3 brane which extends along an R3 inside this R5 here, just as it would have before. But now the position on the Riemann surface is allowed to depend on the radial coordinate R. That's really the only thing that is allowed by preserving these symmetries. So more pictorially, we have our disk and we can add to it the radial coordinate of ADS6. We have an ADS6 sitting at each point, so we might as well include it. And the idea now is at the conformal boundary, we start at the location of the conformal defect. As we move into the bulk, the D3 gets to wander around on the Riemann surface and basically do what the BPS equations allow it to do. So in more concrete terms, we have an embedding which is parameterized by some complex coordinate W on the disk as a function of the radial coordinate here. And we can use the usual ADS-CFT machinery to figure out that turning on such deformations corresponds to relevant operators with dimension 1 or 2, depending on standard or alternative quantization. And we can go ahead and solve the BPS equations with this kind of ansatz. So here I'm just giving you the solution. This is already fully integrated. So this is now a relation between a plus and a minus bar, which depends on the radial coordinate, generalizes the previous BPS conditions, and is an implicit equation for W as a function of R with a complex mass parameter M, which we will look at in a moment. All right, so this is the general form of the equations, and we can now go back to our sample solutions again, the plus, the Tn, and the Yn theories, and we find a set of flows where for each brane web, for each solution, we have a two real parameter family of deformations where the D3 flows along these blue curves which go along here. And we see that there are basically two classes of these curves. Some of them end on a general point on the boundary of the Riemann surface. At that point, the S2 in the geometry collapses to form a closed internal space. And the other embeddings flow into the poles, which represent the external 5 branes. Another crucial point is if we look at a semi-infinite D3 piercing the 5-brane web, we have only one D3 in the holographic dual. And since it does not wrap this S2 here, it cannot end on the boundary of this Riemann surface. It's not allowed to just go up and smoke and terminate there. So regularity requires that a single D3 brane has to flow into the poles in the supergravity solutions. And we therefore find that the mass deformations are again dictated by how many poles we have, precisely matching with the brane web picture. If you were to take a 5-brane junction and pierce it from both sides with D3 branes, to basically have a full D3 intersecting the 5-brane junction, you would be allowed to move it freely away from the intersection point. And in line with that, these curves which end on the boundary of sigma can be made sense of if we allow for 2 D3 branes on antipodal points of the S2. But for a single D3, which is what I want to focus on here, these are not legal. Okay, so what we have is a coherent picture with the 5-brane web story. We have one 3-dimensional defect for 5D SCFT. We have matched the symmetries, and we have matched the number and type of relevant deformations of this defect. All right, so that was for planar defects. That was nice for matching to the brane web picture, but the idea is then to switch gears and look at spherical defects again, which is what we will be interested in later on for doing localization calculations and for extracting in a meaningful way the sphere-free energy. So the idea is basically rinse and repeat, look at spherical defects extending along S3 inside of S5, and look at defect or G flows. This is now really different, unlike for the conformal defect where sphere and planar is just related by a coordinate transformation. Turning on a constant mass deformation on S3 preserves different isometries than a mass deformation on flat space. So things really change here. We have different isometries preserved in different BPS conditions. That makes the whole analysis a little harder. And there is an additional subtlety, which is that generally speaking, SUSY QFTs on spheres are not reflection positive when they're not conformal. They would be non-unitary if we were to analytically continue them to the Sitter space. And in very practical terms, it means if we turn on mass terms, they come along with curvature couplings required to preserve supersymmetry and also have imaginary coefficients. So somehow reflection positivity is down the drain, and the holographic dual needs to know about this. In our case, we only have a mass deformation associated with the D3 brane. So somehow the D3 brane has to know about this imaginary curvature coupling. And this is reflected in relaxed regularity conditions. Unlike in the planar defect case, where we have one complex embedding function characterizing the embedding, the localization of the Riemann surface, we now have to allow W and W bar to be independent embedding functions, which are not anymore related by complex conjugation. This is an example for the plus theory here, where I'm just plotting the real part of W and W bar, not to explain in detail, just to highlight that these are really independent functions now if one goes through the BPS conditions, properly solves them, and then finds the embedding. This is a lot more work than for the planar defects, and that's what the details, that's where the details, for the details I just referred to the paper with Leo, and just give you this general rundown of how the calculations go. Aside from these subtleties, they are straightforward extension of what we've done for planar defects, and we look at the actual free energies in the localization part later. Okay, so this almost concludes what I wanted to tell you about the ADS CFT side of the story. Before going to the gauge theory part, I want to highlight one more piece of information which we can extract from the holographic duals. And this is based on the idea that we can define a very nice set of coordinates on the Riemann surface. This goes back to studying Wilson loops in the 5' webs and in the holographic duals and connecting the two pictures through localization calculations. At the end of the day, what you find is that there is a coordinate system on the Riemann surface which has a sharp meaning in the brane web, which is associated to a given solution. So on the brane web, we can define a discrete set of coordinates in the horizontal direction and the vertical direction, which just label the closed faces in this brane web. We call them an X and an Y. And then there's a coordinate system on the Riemann surface, which can be translated to these discrete coordinates on the brane web. If I take a point on the disk, the values of the holomorphic functions A plus and A minus bar specify for me the coordinates of the face which this point corresponds to in the brane construction. It's shown here for the plus theory and for the TN theory, just to give an example. And what we can do now is we can ask, well, give me your conformal D3 brane defect, which face in the brane web would that naturally correspond to? And from that, we can then get a first clue which gauge node in the quiver diagram this conformal defect might be associated with. For the plus theory, the D3 was in the center of the disk here, and that corresponds to a gauge node halfway along the linear quiver. So we have a linear quiver, all identical rank gauge nodes, and the D3 sits at the central gauge node. For the TN theory, we had a quiver which starts with a small rank gauge node and then has increasing rank to a large rank gauge node. And the D3 defect sits 2/3 along the way between these two endpoints. For the YN theory, it's again the central gauge node in the quiver diagram. So this is not in any way a sharp derivation for any tremendously meaningful statement, but it gives us a first hint and a clue as to what we might expect if we wanted to describe this in gauge theory terms. And that's what I want to come back to later. All right, that should conclude then the ADS CFT part. I hope, Antoine, was this the flow part? Did that address the?
Yeah, yes, perfect. Thanks.
Very good, very good. So asking gives me a moment to readjust here, and I don't want to switch gears entirely and just forget about brane webs, forget about ADS CFT, and go to gauge theory. So we're going to look at 3-dimensional defects and 5-dimensional theories. We have seen some concrete examples already. The general picture is that if these 5D CFTs we've talked about, which have holographic duals in type 2B, they have gauge theory descriptions. They take the form of a linear quiver gauge theory with a large number of gauge nodes in the large n limit. And every gauge node may have flavors attached to them, may have Chern-Simons terms. And that way we get a set of discrete data specifying the gauge theory, which we can infer from the 5 range larges. And the idea now is to just take this gauge theory and add some three-dimensional matter to a particular gauge node, which we single out among the nodes in the Quiver diagram. So what we're doing is we add a 3D chiral antichiral pair in the fundamental representation to some particular gauge node, and that's represented here by this gray box in the Quiver diagram. All right, so I want to really focus on the gauge theory part here, but if we were to look at these through the brainweb lens, the idea would be is if we take a resolved 5 brain web describing a gauge theory, and we poke this with a D3 brain at one particular gauge node, we have the D3, D5 strings connecting the D3 brain to the stack of D5 brains representing a particular gauge nodes. They give rise to a pair of chiral and antichiral matter fields, and this is the leading contribution of this D3 brain in the large N limit. Since we have a large number of D5 brains, this is a large number of fields, and that's the leading contribution. All right, and now the idea will be to do localization computations and compute the free energies for these kinds of gauge theory and see what we get. From a general perspective, as long as we're talking about gauge theories, the ambient field theories flow. There's no notion of conformal symmetry or a distinguished defect, which would be conformal in some way. But one may wonder, I can take the whole thing and flow it to the UV by running all these gauge couplings to infinite coupling and see if that can be related to the conformal defects we've been studying in the 5D superconformal field theories. That's kind of the general idea. But for a start, let me talk about calculating free energies for these kinds of gauge theories. So the vehicle to calculate these free energies is supersymmetric localization. And I want to give a very bird's eye kind of view on how the calculations go before giving the results. So at a very general level, localization allows us to reduce path integrals to matrix integrals. Basically, for each vector multiplet, we get an integral over constant values for the adjoint scalar in the vector multiplet. So we're integrating on the Coulomb branch. And we have a lot of technology, of course, to solve these kinds of matrix models. Now, for the theories I've introduced here, for these long quivers, we have a large number of gauge nodes, and that means we have many matrices. We have many adjoint scalars and many matrices which we're kind of integrating over. And they are coupled to each other by the bifundamentals which connect the different gauge nodes in the Quiver diagram. So instead of one matrix model, we get some kind of multi-matrix model where we integrate over a large number of gauge nodes and have an integrand, which includes the classical action and the one-loop fluctuations, basically. So this is a bit of a non-standard large N limit, but it can nonetheless be solved. And the idea is we take the usual steps, we replace matrices by their eigenvalues and integrate over those. And then we introduce for each matrix, for the eigenvalues associated with each matrix, an eigenvalue density to describe this in an efficient way at large N. And now we have a family of eigenvalue densities labeled by a little parameter T, and this family becomes large in the large N limit because we get a large number of Quiver gauge nodes. And then the idea is to replace this family of eigenvalues with one function of two variables, little z here, which is a continuous version of the gauge node parameter. So this is the central object of interest here. This one function of two parameters is what we're after in the large N limit. And with sufficient massaging, the saddle point equations can then be brought into the form of an electrostatics problem. What does this look like? Here's the general picture. The idea is we have, for each quiver, we have an electrostatics problem in a cavity. The left end of this cavity corresponds to the left end of the quiver and the right end to the right end. And in between, we have ingredients like point charges, boundary conditions, some conducting plates, and they represent unbalanced nodes, flavors at interior gauge nodes, and Chern-Simons terms. Each of those has a representation as one kind of ingredient in this kind of construction. And then by solving this electrostatics problem, we can find the saddle points for the matrix models associated with a given quiver. Here are some pictures for the three theories we've been looking at, the Tn theory, plus and Yn. You see that the Tn theory has a large number of flavors on one end. The plus theory has a large number of flavors on both ends, and these are represented here as sources in this electrostatic potential. For the y-end theory, the central node had some interesting stuff going on. It had a Chern-Simons term, was unbalanced. That introduces this conducting plate down here, the charge at the end. So there's a precise correspondence which can be made sharp and precise between these different ingredients. And based on these, so basically every slice through one of these potentials here is the eigenvalue distribution for one gauge node. All right. Once we have that, we can calculate the free energies and reproduce the 5D free energies we've looked at before. So that's the starting point. That's as much as I want to say about it. And the idea now is to incorporate defects into these 5D matrix models. Now, from a general perspective, we want to couple additional three-dimensional matter degrees to the 5D quiver. And that's a bit more than inserting an operator. We actually have new degrees of freedom. But since we're not adding vector multiplets, we actually do not introduce new integration variables. If we write the 5D matrix model as an integral here over all the different gauge nodes and the 5D integrand, the only thing we have to take into account for these extra 3D degrees of freedom are the one loop fluctuations around this localization locus, which are added by the 3D degrees of freedom. So that's basically the object we need to study, and the slight generalization is what we need to figure out how to deal with. That's fortunately made fairly straightforward, since there is an analog of this probe limit we discussed in the supergravity solutions also in the matrix model. The idea is that the leading contribution of these 3D fields is small compared to the contribution of all the 5D fields. And so they do not perturb the saddle point equations substantially. And the leading contribution of the 3D fields can be obtained by just evaluating the one loop determinants on the old 5D saddle point as we know it. So that's the name of the game, evaluating these free energies. These one loop fluctuations can be taken from genuine 3D calculations. So we have everything to assemble this matrix model. All right, without further ado, here are the results. We have for plus, Tn, and Yn, a bunch of free energies. They look somewhat similar to what we had before. There's some quadratic large numbers here, polylogs, but we have an additional parameter here, which is this little z naught, and that was the parameter which tells me which gauge node is the defect matter attached to. And so we suspect some non-trivial dependence here, and that is indeed the case. So on the bottom line here are just plots of these functions I'm giving you on the top part of the slides, for the plus theory, the Tn theory, and the Yn theory. On the horizontal axis is the gauge node, and on the vertical axis is the free energy. Clearly, this depends on the location of the gauge node. And I should say, which I forgot, that the solutions for the matrix model and the explicit constructions I have given you here are already for the limit where we have flown all the 5D gauge couplings to infinite coupling. They're already gone. So we have the 5D theory at this point. Okay, good. Hopefully that wasn't too bad, but the idea is now we have our 3D, 5D mixed gauge theories, and we have the free energies. And this is what the result is. Clearly depends on Z naught. Is fair game. That's some calculation to do. But we can certainly wonder, this is not what we found for the conformal defects in the 5D SCFTs. So what we would want to do is now take these results, which we obtained from the gauge theories, and connect them in some way to the conformal defects we discussed in the brainwave and holographic pictures. So to make sense of that, I want to go back to the brainwave picture and a slide I've shown before. We have our conformal field theory with a single defect, and we have our gauge theory brainwave, where we can slide the D3 along the entire brainwave, and these kinds of deformations moving the D3 around in the vertical and horizontal directions correspond to relevant deformations. And we can, in particular, in some way slide the D3 from one gauge node to another by moving it along the NS5 branes here, along the D5 branes here. And in that way, connect defects at different gauge nodes through our G flows. So given that we have a 3D defect F theorem, we would then certainly expect the conformal defect to sit kind of at the top of the food chain. That has to be the defect with the maximal free energy from which we can then flow to defects at other gauge nodes. And that motivates some F maximization prescription where the ansatz, the proposal is that the conformal defect free energy can be obtained by maximizing the free energies we calculated in gauge theories over the gauge node to which the defect is attached. That's a fairly straightforward exercise. We have these plots, we're looking for the maximum, and searching for these maxima indeed leads to an exact match between the field theory and string theory calculations on the nose, analytic calculations which match. And moreover, the maxima are precisely at the gauge nodes which we expected from these brane web coordinates in the holographic description. We had a set of coordinates on the Riemann surface which allowed us to identify a particular gauge node. And that was precisely the node which we find from this maximization principle. So that's basically the way in which I want to connect these gauge theory calculations to the string theory calculations. From there, move on to my last slide, which is now we can ask for defect RG flows. We have identified our conformal defect in some sort of gauge theory description. And we can now ask, can we, in addition to matching the free energies for conformal defects, also match the free energies for defect RG flows? And the one mass deformation which we immediately have in the gauge theories is just to turn on a 3D flavor mass for the matter we added at a particular individual gauge node. And we can calculate the free energy for that. We find, once again, free energy quadratic, two large numbers, polylogs, and now we have an additional parameter mu, which represents the 3D flavor mass that we introduced as a mass deformation. And the claim then is that these calculations, again, can be matched on the nose to holographic calculations, the ones which I just outlined, which are in this recent paper, where we look at defect RG flows on S3, turning on mass deformations. And they agree on the nose with these analytic field theory results, which we got from the matrix models. This is for the plus n and the Tn theories. For the Yn theories, the story is actually more interesting. There is a non-trivial phase transition in the free energy, which has to do with the fact that the central node is unbalanced and we have a Chern-Simons term there. There is a critical parameter for the mass, which separates two phases for the free energies. And those, again, match precisely on the nose between string theory calculations and localization calculations. I don't want to say much more about it. The main point here is that they match. Okay, and that's what I wanted to tell you. Let me summarize. I basically have said all this already. We talked about the string theory description of three-dimensional defects in 5D SCFTs, got defect free energies for conformal defects and defect G flows. Did a similar exercise in gauge theories where we took a particular set of defects which one can add and studied those using supersymmetric localization. And we connected these two descriptions to a form of F maximization, which is for flows from the infrared to the UV, so to speak. It's different from the usual F maximization in 3 dimensions, but that's goes nicely with the fact that we're just looking at a different set of flows. Okay, thank you.
All right, let's thank Christoph. Questions?
I had another question at some point. No, I don't remember exactly, but the number of D3 branes. Oh yeah, it was when you were counting the number of degrees of freedom. But then at the end of the previous part, you said if I put two D3 branes, then I can, yeah, they can end on they don't have to end on the
Right.
poles, but they can end anywhere. And then how does the number of degrees of freedom work in this case? Because it seems you have infinity. Or...
Oh, very good. Yeah, let me, so the picture I'm having in mind is if we take this kind of cartoon where D3 pokes the junction and we add another one from the bottom so that we can form one complete D3.
Ah, from the bottom. Okay, so then of course you can go anywhere. You can
then you just can take it anywhere, right? There's no more constraint.
But if
now,
you put from the top,
sorry, say that again.
If you put two D3 branes from the top.
Ah, very good. At some level, for the leading result I've told you about here, it doesn't really matter. So let me start from if you add a second D3 brane here, what we have done is we have a small number of D3 branes, large number of 5 branes, and then we use the probe approximation to calculate the free energy. And as long as you're doing that, you can add as many as you want until they start to back react. You basically just is an additive overall.
Yeah. So on your graph later, they both have to end on the pole and nothing is different.
Very good. So for the graph here, this one is what you're having in mind?
Yes, yes.
So what you can have is so with a single D3 brane, let's say this curve here, it's not a legal curve because the D3 can't just end here. If you have two D3 branes which sit at antipodal points of the S2, they can meet here basically. It's like you take a sphere and you slide the D3 through a sphere.
Okay, so it's this antipodal point. It's the antipodal condition on the S2, which tells you that the D3s were actually on each side. Okay.
Exactly, exactly. If you were to add two D3s from the same side, you would still have the same space of deformations.
I see. Yeah, thank you.
Do we have more questions? Well, you were very clear. So then let's thank Christoph again.
Thank you everyone for showing up.
And we can go off the record.